Hello, everyone. My name is Simon Shao from Rome Lab at the University of Michigan. I'll speak about reachability-based trajectory safeguard, which is a new technique to safely train and utilize reinforcement learning during motion planning. Ensuring safety while performing real-time planning is challenging, since sensor horizons in autonomous systems are limited. A common strategy to solve this problem is to rely on receding horizon planning, in which we replan while we move. Such a planning framework usually utilizes a tri-level hierarchy to balance optimality and speed. The top level is a global planner that proposes waypoints to achieve a high-level objective. Next is a trajectory planner, which proposes a trajectory that avoids obstacles to get to a waypoint. Finally, there's a tracking controller that minimizes the error when following such a trajectory. However, this approach can sometimes create unsatisfactory behavior. The high-level planner has to be hand-tuned, which is hard to guarantee good performance across a wide variety of environments. The trajectory planner lacks an understanding of the global goal, causing it to sometimes make short-sighted decisions. Our approach uses an RL agent to take the role of both the high-level planner and the trajectory planner. Such an RL agent takes the robot state, local obstacles, and global goals as observations and encodes making progress towards the goal as a reward function. Lastly, it outputs reference trajectories for the tracking controller. However, such an RL planner may not be safe even after training. Thus, we use reachability-based trajectory safeguard that acts as a shield to ensure the safety of the dynamic system during learning and subsequent operation. Using RTS, we are able to achieve real-time safe planning and reduce training time by reducing the task complexity. A wide variety of methods exist that attempt to ensure safety of a control policy constructed using reinforcement learning. Broadly speaking, there are three types of safe RL. Many model-free RL methods try to update a policy safely without using a dynamic model. Without such a model, these methods never actually ensure safety and typically only guarantee near constraint satisfaction. And another line of work focuses on learning an accurate model of the system. By ensuring such updates align with the data seen in the previous rollouts, safety or stability can be ensured by using traditional control methods such as Hamilton-Jacobian functions, control barrier functions, or Lyapunov functions. However, these methods usually work only for low-dimensional systems. Lastly, shielding methods use ground truth dynamics to ensure safety. Such a shield makes adjustment to the action of a RL agent output that may cause a collision. However, since the fall dynamics is complex, shielding is usually too slow for real-time applications. To deal with such problems, others use linearization or discrete action space to speed things up. But our method, RTS, makes no such compromises, and it guarantees constraint satisfaction, can be used for highly nonlinear systems, and use an offline-online combination to ensure real-time safe planning. Now let's see how RTS works. In RTS, we compute a forward reachable set object offline and use this FRS online to ensure safety. In this section, we also briefly introduce RTS's predecessor called RTD, which we used in the result as a comparison. During offline of RTS, assuming we know the ground truth model of the robot, we compute a forward reachable set for a full family of trajectories that the robot may take. When we specify the trajectory parameter values to determine a single reference trajectory, the FRS we computed can be reduced in size very quickly, obtaining a more accurate FRS. Equipped with that information, now we can use the FRS to safeguard our actions online. During online planning, we train a model-free RL agent to output actions as trajectory parameters, shown in orange. When we know the proposed trajectory parameters are not safe, we adjust the trajectory parameters to a close one, determining a new reference trajectory, thus ensuring safety. In summary, we use reachability to ensure only safe reference trajectories are sent to the robot. In our previous work, RTD, we used a very similar method to ensure safety. However, instead of using an RL agent, we used a custom-tuned global planner to propose waypoints, and used nonlinear, non-convex optimization to select the best safe reference parameters. Compared to that method, our RL agent has a more holistic view of planning and avoids issues that occur due to the two-step hierarchy. Now we present the simulation experiment result demonstrating RTS in comparison to a baseline RL agent and RTD. We specify our task as reaching a goal at the far end of the environment, and we use a reward function that rewards avoiding obstacles and making progress towards the goal. Let's see how RTS performs in our car lane change task. The top animation shows RTS plus RL compared to the baseline RL in the same scenario. The striped yellow and black lines are reference trajectories proposed by RL, and the solid black lines are safety insured reference trajectories using RTS. The baseline RL agent crashes while RTS successfully corrects the unsafe behaviors. We see that with the help of RTS, we can reach 100% of the goals, while baseline RL reaches 82% and RTD 90%. In terms of speed, the first row shows that all three are fast enough for real-time operation, with the additional benefit that our proposed methods avoids the optimization step in RTD that takes an unpredictable amount of time. Now we show the training plot of the two agents. Notice that during training, with the help of RTS, the agent gets to a higher reward in much fewer episodes. Additionally, RTS plus RL has 0 crashes during training. In the drone obstacle tunnel task, we similarly want a drone to navigate towards the end of a tunnel. Notice that in the table below, with the limited amount of training time and the limited complexity in the network, the baseline RL won't train to get towards the goal, while RTS does and performing better than RTD. The training plot also tells the same story. Using this experiment, we show that by having RTS, our proposed method can solve a harder tasks with the same amount of computing resource. All in all, we have built a safety layer that ensures safe, real-time motion planning for RL training and deployment. We hope this work can help people reduce training time and help deploy RL-based motion planning in the real world. We thank the following sponsors listed here, and there are more content in the GitHub page that you can find using the QR code below. Thank you for your time.